Hello everyone, welcome to lecture 34 of the NPTEL course on Riemannian geometry. So in the previous lecture we set up this notation and nomenclature of admissible paths, admissible vector fields along admissible paths, then admissible variations and admissible vector fields along admissible variations, right. So this is all to set up this variational problem of trying to optimize the length and the energy functionals, right. Okay, so I ended the previous lecture with a certain remark which I would now like to explain before we move on to the main topic of this lecture, namely the first variation formula. So recall that we defined the admissible variation to be a function from minus epsilon to epsilon cross a comma b to m, such that there is a partition of a to b such that gamma restricted to this interval minus epsilon to epsilon cross the closed interval ak minus 1 to ak is smooth. And then our notation was that we denote by del s gamma the velocity vectors of the transverse curves and del t gamma to be the velocity vector of the horizontal curves, right. So a consequence of the definition is that if you look at the transverse curves, they are actually smooth for every t, okay. Unlike for instance the horizontal curves, even if you fix an s, the horizontal curve is only piecewise smooth, it is not smooth, right. It may not be completely smooth. On the other hand, the transverse curves are always smooth, and then I also claimed that if you look at the velocities of the transverse curves, they form a continuous function. So this is of course trivial from the definition in the variable s, and even in the variable t this is trivial for all t not equal to the problem points ak, right. So now let us try to see that this is also continuous if t is one of these problem points ak. Okay, so let us consider the following. So we have our ak here, we have ak minus 1 here, and let us say ak plus 1 somewhere here. Now by the definition of smoothness we are fixing an s. By definition of smoothness there exists a smooth extension, let us call them gamma minus to the left of ak and to the right of I mean to the left of this interval and to the right of this interval, right. So we have these extensions to the interval ak minus 1 minus delta to ak plus delta and ak minus delta to ak plus 1 plus delta respectively, right. Okay, so now what will be the limit as t approaches ak from let us say the left of v of st. What was v of st? That was simply the s derivative of gamma st, but since we are approaching ak from the left, I might as well look at the extension of gamma to the left of ak, right. So this is the same as the limit as t approaches ak ak of the smooth function. Okay, but now because you are computing the s derivative for the smooth function, you can simply plug in s comma ak, okay. But because this is an extension, note that this function is equal to gamma of s comma ak, right. So So this derivative is simply going to be the derivative of this at ak, right, because remember if you fix a t and let s vary, then the resulting thing is actually a smooth function of s, right. So this derivative makes sense, but now by symmetry, clearly by symmetry you see that the limit as t approaches ak plus of v of st is also the same thing. Okay, so in other words, the two limits coincide, and hence this is a continuous function even at t equals ak. Okay, so that was to clarify the remark from the previous lecture. So now let's move on to the main topic of today's of this lecture, namely the first variation formula. Okay, so here's the statement. So let gamma be an admissible curve. Okay, let capital gamma be an admissible variation with variation vector field v of t. So if you recall, the definition of v of t was that it is just del s of gamma evaluated at s equals 0. Okay. Then we have the following formula. If you take the energy functional along these horizontal curves and compute the derivative at 0, this is given by the following. So you have some terms coming from the boundary, right, and then you have some correction terms coming from the fact that that your gamma is only piecewise smooth and not smooth. So you will have correction terms that look like this. Okay, remember delta k of gamma dot was the jump in the velocity vector at ak, and then you get the principal term which is v of t times the intrinsic acceleration of gamma. You integrate that on the interval a to b. Okay, so again a remark is that from now on I am not going to keep making this remark, but whenever you see integrals of this type, so whenever you see an integral of this type, that basically just means summation from k to k from 1 to m, integral from on this interval where gamma is smooth. Okay, so this is the statement of the first variation formula. Alright, so in order to prove this, I need the following lemma, which is called the symmetry lemma. Okay. So this says the following. So let capital gamma be as above. So it is an admissible variation of little gamma. Then if you take del s gamma, that's a vector field along capital gamma, and you take its velocity, you take the covariant derivative of that vector field in the horizontal direction, well, that will be the same as taking the velocity vectors of the horizontal curves and then taking the covariant derivative in the transverse direction. Okay, so the claim is that you can interchange del s dt and ds del t. Okay. So the proof is easy if you use local coordinates. So computing at a point at some point p, with local coordinates, let us say x1 up to xn. So, in these local coordinates gamma s comma t, in these local coordinates is basically just x1 of x comma t, s comma t, etc., up to xn of s comma t. Okay, so then what is the covariant derivative ds of del t gamma? So, this is the RHS. Well, this is simply ds of what is the velocity vector of the horizontal curves, that is just dxk by, sorry, let me dxk by dt in the kth direction, right. But then the covariant derivative along the curve is simply given by taking the derivative in the s direction plus some terms that come from the Christoffel symbols, right. So, you will have dxi by ds times dxj by dt, okay, this whole thing times del k. Alright, but now if you do the same thing but with the other order, so if you take del t ds gamma, so the first term will so all of these should be partial derivatives. Let me correct the notation, right. So this will then just be del square xk by del t del s plus gamma ijk del xi by del t del xj by del s, okay, the whole thing times dk. But now you can just interchange the role of I and j. So this is simply this, in order to compare it to our earlier formula. Sorry, this will be ji then. Right, but now you notice that this thing is equal to this thing because our connection is symmetric, right. The Christoffel symbols, because our connection is torsion free, the Christoffel symbols have this symmetry. So, these two expressions are basically equal, and that proves the symmetry lemma. Okay, so now I am going to use this to prove the first variation formula. Okay. So, recall the definition of the energy functional. The energy functional of gamma s was simply half times summation k going from 1 to m integral from ak minus 1 to ak of gamma s dot of t whole squared. Okay, so now if you differentiate in s, because on these subintervals everything is nice and smooth, you can pass the derivative inside the integral sign. Okay. So, instead of gamma s dot, I will use the following notation. Del t of gamma, right. Okay, so now if you pass the derivative inside, that's going to be by the fact that this is a metric connection. This is going to be the following. Sorry, I have a half here, right? It's going to be 2 times the integral from ak minus 1 to ak of ds del t gamma comma del t gamma. Okay. So the 2's cancel. Okay. So now let's analyze this term. Yep. So by the symmetry lemma, so this is where I am using the symmetry lemma. This is the same as the integral from ak minus 1 to ak of dt del s comma dt gamma. Okay. All right. So now let's look at this term. So the idea is I want to take, I want to take the time derivative. Let me correct this. Right. So this is dt ds gamma. So the point is I want to take this time derivative and move it outside the inner product sign, right. So for that we note the following, that if you take d by dt of del s gamma del t gamma, then by the fact that we are dealing with metric connections, this is going to be dt del s gamma comma del t gamma plus del s gamma comma dt del t gamma. Okay. So in other words, we have this inside the integral. We can now express that as the difference between this term and this term. So that is what we will do. So d by ds of the energy functional is now given by summation k going from 1 to m of 2 terms. So the first term is basically just a d by dt of del s gamma comma del t gamma, okay, and then minus k going from 1 to m del s gamma del t of dt of del t gamma. Okay, so now let's right. So let's plug in s equals 0. So at s equals 0 we get the following. V of t times gamma dot of t minus you get this integral term, integral a to b of v of t times the intrinsic acceleration of gamma. Okay. So the this term is good because this is there in our formula, in our first variation formula. So let's analyze the first term. So in the first term I am going to use fundamental theorem of calculus. Right. So the first term is equal to the summation k going from 1 to m of v of ak times gamma dot of ak from the left. Remember, gamma dot is not smooth at these ak's, right, and minus V of AK V of AK minus 1 at the other endpoint times gamma dot of AK minus 1 but from the positive side, the right side limit. Okay, so now let us write all of these out. So when m is when k is equal to m, so that is the sort of rightmost extreme term. This term is just V of B times gamma of B minus V of AM minus 1. So maybe let me write a bit smaller so that it fits in one line. So this is going to be V of B times gamma dot of B minus V of AM minus 1 gamma dot of AM minus 1 but from the right. Okay. Okay, now when k is m minus 1, you get V of AM minus 1 gamma dot of AM minus 1 but now from the left, right, minus V of AM minus 2 gamma dot of AM minus 2 from the right. Alright, so the point is that if you combine these two terms, so the blue terms can be written in a concise fashion as simply this with the jump in the velocity vector at AK but with a minus sign, okay, because the jump, remember, is defined to be gamma of this is AM minus 1. Sorry. Okay, because remember the jump is defined to be this plus minus this minus. Okay. So all the cross terms will now start telescoping and they can be combined into terms of this type, and you are left with then the final boundary term. So the first term can be now simplified to, you will have the two boundary terms which do not have any counterparts, but then the rest of the terms you can combine them into this summation. Okay, and that completes the proof of the first variation formula. Okay. Alright, so this is about the energy functional. What about the length functional? So for the length functional we have the following remark. If gamma is normalized so that gamma has unit speed, then in fact, so this is, maybe I will write this as a claim. So then the claim is that the derivative of the length functional actually agrees with the derivative of the energy functional. Okay. So what is the proof? So remember the definition of the length functional. So d by ds of the length functional is simply d by ds of the integral from a to b of the speeds right. So, you can again take the derivative inside, and now we use this formula that if you have a function f, if you take the norm of that, this is the same as 1 by mod f times the derivative of the square, okay, with a half. This is of course elementary from chain rule, but applying this we basically get the integral from a to b of d by ds s equals 0, we get 1 by 2 gamma s dot of t, and you plug in s equals 0 times d by ds of the squared. But now this term right here, because we are assuming unit speed, this is just 1. So, this is precisely half d by ds at s equals 0 of the speed squared, but that was of course just the energy functional, okay. So, that completes the proof of the claim. So, at least as far as first variation formula goes, as long as you normalize your curve to have unit speed, there is no difference between the first variation of the length and the first variation of the energy, but you need to have this additional normalization. This is why I mean, this is one of the reasons why working with the energy functional in this whole theory is much more advantageous, because then one does not have to keep worrying about such normalizations. Alright, so that is it for this lecture. In the next lecture I will talk about the consequences of the first variation formula, and we will actually show how geodesics naturally arise as critical points of the energy functional, okay. So, that is what we will talk about in the next lecture. Thanks for your attention, and I will see you next time around. Thank you.